calculating the power consumption of an electric circuit appears to be relatively straightforward. You just multiply the voltage by the current. Although there might actually be more to it than that. Let's say that I have a light bulb, and I wire up this light bulb to an AC power outlet, so a standard 240 volt AC outlet. Now, if I take a look at the voltage that is being applied to my light bulb and I plot it out in a graph, then of course what I get is a sine wave. And if I take a look at the current running through my light bulb, I also get a sine wave, be it a slightly smaller sine wave. But you can see that it's exactly in phase with the waveform of my voltage, which means it has the same timing. So when the voltage goes up, the current also goes up, and when the voltage goes down, the current goes down again. When the voltage goes negative, the current also goes negative, which means, of course, the current reverses. You get the idea. And so our formula, which was power is equal to voltage times current, applies really well here, because at any given moment in this graph, I can say, well, this is the voltage, this is the current, I multiply them together, and I get the power consumption at that specific moment in time. If I were to perform this calculation for every single point on our graph, I would get a new graph, which is the power graph. So as you can see, the power is also a sine wave, but this sine wave never becomes negative, so the power is always positive. And that makes sense, right? Because even when the current and the voltage are both negative, I'm multiplying two negative numbers together, which becomes a positive number. And this also makes sense in the real world, because even though the voltage on the light bulb might be negative at some point, and the current might be reversing direction, the light bulb doesn't care about that, right? The light bulb produces light regardless of the direction of the current and the voltage being applied to it. So even when the voltage and the current are negative, it's just consuming power and producing light. And then what we can say is, well, we have this power curve, or we have this power sine wave. We take the average value of that, and now we have the power consumption of our light bulb. And that might be something like, I don't know, 50 watts. Let's say it's a 50 watt light bulb. I don't know. So this is fairly straightforward. Unfortunately though, not all components are like this. Not all things are like light bulbs. In fact, most things are not like light bulbs. So let's imagine we're connecting something else to the AC power outlet this time, okay? We're not going to specify exactly what it is, okay, because it doesn't really matter for this video. We're connecting a mysterious box, basically, and we look at the voltage waveform. It's just a sine wave because it's still the AC power outlet that is connected to it. And we also look at the current, and it looks kind of strange, right? Because, yes, it's still a sine wave, and it still has the same magnitude as the current in our light bulb, the same amplitude, I should say, but it's no longer in phase, right? It doesn't have the same timing as the voltage anymore. There is what we call a phase shift between the voltage that is applied to the circuit and the current flowing through the circuit. And this actually happens with many different kinds of machines that we attach to power outlets. And exactly why this happens, we're not going to go into in this video in detail, but this is just for some reason a machine or a thing where the current and the voltage are not in phase. And that makes for a very interesting situation. Okay, so let's try to apply our power formula again. Okay, so we apply it at this point, for example. So we have a certain voltage, a certain current, we multiply, we get a certain power. Okay, that works. Now let's try it at this point. We have a negative voltage, a negative current, we still get a positive number for power. But now let's try it here. Okay, so here we have a negative voltage and a positive current, which wasn't possible in the light bulb, but now it is, because voltage and current are no longer in phase. And so, now we have a negative number multiplied by a positive number, so we get a negative number for power. That's weird, right? What is negative power consumption? Well, if you think about it, negative power consumption means that we're supplying power. So apparently, when this machine is at this specific point in time, it's supplying power back to the power outlet, okay? So now it's consuming negative power, which is another way of saying it's supplying power back to us. And again, if we go ahead and calculate the power usage for every single point in our graph, we get the power sine wave. But the power sine wave now is different, right? Because now it's got negative values. And in fact, now its average value is 0. Because the amount of time that this machine is taking power from us is equal to the amount of time that it's giving power back to us. And so the net power consumption of this machine, again, whatever it may be, is apparently 0. It's not using any energy at all, okay? Which is kind of strange, but it is actually what's going on. Now, if we just look at the magnitude of the current in the wiring and the voltage being applied, then the system still appears to be using 50 watts of power, just like our light bulb, because the magnitude of the voltage and the current are still the same. But if we take into consideration this weird phase shift going on, then we see that the system is in fact not using any power at all. And this is where the terms apparent and real power come in. Apparent power is the power that something appears to be using based on just the magnitude of the current and voltage. Real power is the actual power consumption of the system if you actually observe its real energy consumption per unit of time. That's what power is. In our light bulb, the apparent power was the same as the real power because the current and the voltage were in phase. In this new machine that we attached to it in the second example, the real power was very different from the apparent power. In fact, the real power was 0, it was nothing at all. This brings us to something very important and something very interesting called power factor. The power factor is a number that we can use to translate between real and apparent power. So to give you an example, in our light bulb, the power factor is 1, which means the apparent power, which is 50, is multiplied by the power factor, which is 1, and that gives us the real power. So 50 times 1 is just 50, which is right because the apparent power is the same as the real power in our light bulb. In our second example, the power factor is 0, which means the apparent power, 50, gets multiplied by a power factor of 0. 50 times 0 is 0, nothing at all, which means our real power is 0, which is right. We've investigated that. And so I can hear you thinking, well, that's all very nice, but how do I even know this power factor? You know, the power, yes, sure, I need to multiply the apparent power by the power factor, but how do we find the power factor? Great question. The power factor can be found by taking the cosine of the phase difference between voltage and current. It sounds very mathematical, but it actually makes perfect sense. Let's take a look at our light bulb again. What's the phase difference here? The phase difference is 0 because they're in phase, they have the same timing. Meaning we take the cosine of 0. What's the cosine of 0? Well, that's 1, of course. So the power factor is 1, or cosine 0. In our second example, the phase shift was 90 degrees. I made it 90 degrees. Cosine of 90 degrees is 0. So here, our power factor is 0. But you could do this for any kind of phase shift. So here we took a look at no phase shift at all, so the power factor is 1, and a phase shift of 90 degrees, where the power factor becomes 0. But it could also be a phase shift somewhere in between there, which will give you a number somewhere in between 0 and 1. In the real world, power factor is often written as cosine phi, because phi means the phase difference that we discussed. So when they write on an electric motor, for example, what its power factor is, they don't write power factor because that's quite long, they just write cosine phi because that's nice and short, and then equals 0.8 or whatever the power factor may be. So anyway, I hope this video made things a bit more clear when it comes to power consumption in AC electrical systems. I hope you've enjoyed this video, and of course, thank you for watching.